Okay, so to continue the course, today we're gonna talk about hull form definitions. So to begin with, I have a small question, like, are you familiar with the different type of hulls? Do you know which shape they can have? Nope, no one? I have no idea what you know what the hull is. Okay, so then I guess we can watch this video that explains shortly the different types of hull.
일러스트 자체가
Types of hulls. Flat bottom boat. They are generally less expensive to build and have a shallow draft. They can get on plane easily, but unless the water surface is perfectly calm, the ride can be rough because the flat bottom hits each wave. They are less stable and require careful balancing of the cargo and crew. V-bottom boat. The V-bottom rough waters, but needs more power to achieve the same speed. Many runabouts use the V-bottom design. Round bottom boat. It moves easily through the water, especially at slow speeds, but tends to roll unless fitted with a deep keel or stabilizers. Many trawlers, canoes, and sailboats have round bottoms. Multi-hull boat. Catamarans, trimarans, pontoon boats, and some houseboats have a multi-hull design. The wide stance gives greater stability. Each of the hulls may have any of the bottom designs described above.
Okay, so now we have
This can
we have an idea of the different types of hull of a boat. And I think it was a good introduction because today we're going to talk about hull form definition and design. Because the very first step in designing the hull of a ship is designing its shape and its form. And it is estimated by various coefficients that are dimensionless numbers that describe hull's overshape characteristics. And these coefficients are ratios of areas or volumes of the actual hull compared to prism or rectangles defined by the ship's length, breadth, and draft. So we're going to talk about these coefficients to begin with. So the first coefficient is called the block coefficient, or CB, and it is calculated as the ratio of the underwater volume of the ship's hull. So on the first drawing, you only have the underwater part of the hull that is underwater. But on this design, you have the whole ship, so basically it's this part. And you divide it by a rectangular box that has the underwater ship's length, width, and height as dimensions. This would be a prism that has this shape. So the coefficients, to give you an idea, here are some values of different CB coefficients. So for the first boat that you see on the picture, which is a rectangular pontoon, the coefficient value is 1 because the shape of the underwater hull is really a prism, just rectangular shape. For the second boat, which is a barge or Great Lake bulk carriers, the CB would be 0.9 because these boats are flat-bottomed boats built mainly for rivers and channel transports of bulk goods. And they have this shape to be able to pass through channels like the Panama Channel and through locks that are very narrow. And finally, this one is a research vessel, oceanographic research vessel, and it has a CB of 0.5, which is a bit low because this ship is very narrow. So we can understand that usually the regular CB for ships is around 0.6, 0.7. And so if you have a high CB, you will be able to have low speed with a high cargo capacity. And with a low CB, you'll have low resistance and a good sea keeping. So sea keeping is the ability of the vessel to withstand rough conditions at sea. Then moving on to the next coefficients, we have the midship section coefficient, Cm, which is equal to the area AM, which is the, like if you take the ship in its length and you cut it in the middle, you have a section. This is the section you can see. So this is this area divided by the breadth times the draft. And you also have a little variation of this coefficient, which is the maximum section coefficient. It's the same one, but instead of taking the section that is at the middle of the ship, you take the greatest section of the ship. So for big ship, the midship section coefficient is usually the same as the maximum section coefficient. But for small ships, it can be quite different. And also, this is the logo of the midship section coefficient, and we just wanted to show you that the Society of Naval Architecture and Marine Engineering decided to use this diagram as their logo, which is a non-profit society that serves maritime and offshore industries and their suppliers in the United States. Then for the other coefficients, we have the prismatic coefficient Cp, which is equals to the volume of the surrounding prism, just the same as we said before, divided by the length times the AX, so it's the same section as I explained also before. And it gives an indication of how much the ship's forms changes at its ends. Then we have the water plane coefficient CWP, which is equals to the area of the water plane. So it's the area of the ship at the level of the water line, divided by the area of the surrounding rectangle here. And it shows how thin and how sharp the boat is. So these were all coefficients that we used to design a ship, but we also use other non-dimensional numbers, like the Froude number. So this number was originally created by William Froude, who defined it in Law of Comparison in 1868. And then later, the naval constructor Frederick Witch transformed it into the 8-dimensional number as we know. So it is used to determine the resistance of a partially submerged object moving through water. So in our case, it would be the ship. It is equals to V divided by the square root of G times LWL. So V is the relative flow velocity between the sea and the ship. G is the acceleration due to gravity. And LWL is the length of the ship at the water level, line level, as the professor explained before. So we have some values. For a 500 feet naval vessel moving at 10 knots, Fn would be 0.13. And for a small ship, 150 feet research vessel at 10 knots to the same speed, Fn would be 0.24. So Fn relates the resistance of an object moving through water. So you can conclude that it is easier for big ship to have a higher speed because their Fn is lower. And before this number was invented, designer of ships used the speed-length ratio, which is pretty much the same but without the G's. So the units were also different because knots were used for speed and feet for length. But with Fn, you have to match the unity of the gravity G, so it would be meters and seconds. Then we have another ratio, which is the displacement length ratio. So it explains how heavy the boat is relative to its water line length. So it is calculated by dividing delta, which is the boat displacement in long tons, and divided by 100 of the waterline length cubed in feet. And it can be used to compare the relative heaviness of boats, no matter the size. And before this number was invented, the Bragg coefficient was used before, so we talked about it a few slides earlier, so it's the same coefficient. And so for the DLR, you can have some values of regular number. A boat would be considered ultralight if its DLR is under 80, 90, but ultra heavy, it's over 360. So here you have some examples for very specific boats, like the Oceanographic Research Vessel that we saw before, would have CLR of 433 and a Great Lake bulk area of 80. And you can also compare the values with the blood coefficients here to have an idea of what number will represent what. Then as designer, it is also really important to know how much cargo can be carried and the buoyancy. But for everything, to know that, to know the coefficients, you always need to know the volume of your hull, of your underwater hull. So before, no computers can do it for you, but before that, two techniques were used. First one is the Ponjon sectional area curve. So the idea is that you take your boat and you do multiple sections. Of course, the more sections you do, the more precise you're going to be, so the better it will be. Like ideally, you should have like an infinite number of sections. But the idea is like you take one section, and it is represented here, and here you have the shape of the hull, and you want to try to calculate the area of this section. Like here it's the half section. And you're going to integrate with AZ. And you can integrate to different waterline levels according to how under the water your ship is. And then, so you're going to have two dimensions, which is it's an area. And then if you add them all together, you have a third dimension, which is the length. And then you have the volume of your underwater hull. And there is also another technique, which is called the sectional area curves. So on the graph, the vertical is the section area, and horizontally you have the length of the ship. So if you integrate the area under the curve, you can have the volume of the ship. And you can also calculate it with the formulas here that use the coefficients that we explained before, like CB, CM, and everything we talked before. And so finally, LCB is the longitudinal center of buoyancy, and LCF is the longitudinal center of flotation. And the difference between the two is that buoyancy is the upward force on the body immersed in a fluid, while flotation is the state of floating. So you will try to calculate this LCB and LCF, even if they are quite similar. Here you can see that the LCB and LCF will vary according to the shape of the forebody and the aft body. So the aft body is the shape at the end of the boat, and the forebody is the shape at the front of the boat. And the forebody will influence wave-making resistance, wave pattern, and braking resistance and seakeeping. Whereas aft body will influence viscous resistance, self-propulsion performance, because the engine is at the back of the ship. Weight distribution is like how the wave is going to be behind you, the shape is going to have once you've passed through it. Cavitation, maneuverability, and engine room arrangement. And so as a designer, you'll be willing to have the optimum LCB, so you're going to use graphs just like that. They use, you're going to have, as an input, you need to have the CB coefficient and the foot number, and then you'll be able to have the optimum LCB and LCF. So through this course, we saw the main coefficients and numbers that you need to have to design a ship, the hull of the ship. And to continue, there's a little video that I can show you that goes a bit forward and also recaps what we've seen.
우리가 보통 코딩을 할 때 모든 코드를 다 적거나 단어 단위의 자동 완성 기능을 사용할 수 있지요. 그리고 사용법이 기억나지 않을 때
As an example, take water lines. If you were to take the waterline plane, make a bunch of different copies of it, and run it from the keel line, which is the bottom of the hull here, all the way up to the top deck, you get these blue lines here. And from the side and from the front, they look straight. right? Because they are horizontal slices of the hull. But if you look at this from the top or from the side, sort of from this oblique view, then you get a sense for the curvature of the ship as it changes from the keel all the way up to the top decks. And so now we say, okay, here's some lines. We can start to see more of how the hull is changing, what its real shape is here. Similarly, if you take the midship section plane and you take a bunch of copies of it and put a bunch forward and a bunch aft, you get what are called stations. The stations here from the side and from the top look straight, which is good. That's what you want. And then from the front or the back or from this oblique view, now you get these sectional curves here. And you can see that they illustrate how the hull is changing as you go from the bow to the stern. Here, you see down below here, like if you were to plot all those red lines on top of each other, it would get kind of busy. It'd be tough to see which ones are going where. So generally, we put the stations that are forward of midships on the right-hand side and stations that are aft of midships on the left-hand side. This way, you can see how things are changing easier. And most ships, almost all of them, have a port-starboard symmetry. So you're still retaining all of the information here.
So if you're more curious about what we talked today, this video, which is the beginning of a course in naval architecture, explain more in details what we've seen, like what type of hull we can have, lines drawing, length, other vocabulary. So I think it's pretty interesting, but pretty long for today. So that's it for me. Thank you for your attention.